So large language models are really hitting this fascinating new stage of self-improvement. And what's truly remarkable, I think, is that this big leap forward isn't actually about another massive, billion-dollar retraining cycle. Instead, they're learning in a much smarter way. They're like watching their own wins and losses in real time and absorbing those lessons instantly. It's almost like the ultimate institutional memory, but created on the fly.
That really nails the core of the research we've been digging into. We take a pretty deep look at this work introducing Agentic Context Engineering, or ACE. And this framework, well, it fundamentally changes how these LLMs use their own context, their memory. We're shifting away from treating context like some static instruction sheet and moving towards something much more dynamic, an evolving playbook, really, built from actual experience.
Right, and that's basically our mission for this deep dive. We're going to unpack exactly why ACE treats an LLM's context like this super detailed, evolving playbook. We'll show you how this, frankly, really methodical approach leads to these huge performance boosts, especially when you're trying to build scalable, self-improving AI systems. The kind that can tackle really complex, multi-step jobs, think autonomous coding or high-level financial analysis. The goal here is for you to walk away really understanding this pivotal shift, how we're building AI systems now.
Okay, so let's break down that foundational idea first. Context adaptation. Traditionally, making an LLM better meant expensive fine-tuning, tweaking the model's internal weights. But the modern, more pragmatic approach, it's context adaptation. Way cheaper, way faster. You get better performance not by changing the core model, but by updating its input context. Things like the instructions you give it, the evidence it sees, or examples of successful reasoning steps.
Exactly. Adapting through context is immediate. It's transparent, you can see the changes, and it's easy to roll out. Plus, it lets lessons learned in, say, one part of a bigger AI system get shared instantly across other parts. That's a massive shift. It fundamentally changes the cost and the speed of improvement. But, as we saw with some earlier tries, faster isn't always better if the method itself is flawed. These prior context adaptation approaches, they hit two major roadblocks, and ACE was basically designed specifically to fix them.
Okay, let's zero in on those failure points, because understanding them is pretty key here. The first one the researchers flagged is this thing called brevity bias.
Yes. A lot of the initial prompt optimization work was, well, kind of obsessed with being concise. They were trying to boil down the best strategy into the shortest possible instruction set. Thinking, a short generic prompt saves tokens works okay for simple things. But when you abstract everything down to just a short summary, you inevitably lose the detailed domain-specific stuff, the heuristics, the practical tips, the kind of insights you absolutely need for complex agents or like specialized knowledge work. Think dealing with tricky financial rules or handling errors in complex software. You just lose that actionable nuance.
Okay, that makes sense. And the second failure mode, this one sounds even more dramatic.
Yeah.
Context collapse.
Yeah, this one is critical and kind of counterintuitive. It was seen in earlier methods where the LLM itself was responsible for rewriting its entire context after each learning step, like a full rewrite. So as the context grows over time, maybe over dozens of steps, the LLM tries to tidy up its memory, summarize it, but often it gets way too aggressive. It compresses the context into a much shorter, less useful block. And this deletion leads to a sharp drop in performance because crucial details, things learned the hard way, just vanish.
And you mentioned there's a really stark example of this context collapse from the paper, right? It shows just how bad it can get.
Oh, absolutely. It's quite memorable. The researchers tracked an agent on the AppWorld benchmark. Its context had successfully grown to 18,282 tokens. Pretty detailed. And it was doing well, 66.7% accuracy. Respectable. But then, because of just one single step of this monolithic rewriting, the context collapsed. And not gradually, instantly, down to just 122 tokens.
Wait, from over 18,000 tokens down to 122? That's like almost everything just disappeared.
Yeah, exactly. Vanished. And the impact? Immediate. Accuracy just plummeted, down to 57.1%, which, and this is the kicker, was actually worse than the baseline performance without any context adaptation at all. The LLM basically threw out its entire brain trying to tidy up. It tried to summarize its whole detailed notebook into, a fortune cookie.
Wow, that is the ultimate technical facepalm, isn't it? Like spending weeks creating detailed study notes for a huge exam and then burning them right before you walk into the room?
That's a really good analogy, actually, and it points directly to the core insight behind ACE. Context should not be some brief, monolithic summary. It needs to be comprehensive. An evolving playbook, filled with categorized domain knowledge, specific examples, learned strategies. The models, surprisingly, are actually pretty good with long, detailed context. They can figure out what's relevant on their own during inference. So the key isn't aggressive compression, it's intelligent curation. and preservation. Right, and that intelligent curation, that's really the engine driving the ACE framework. ACE
Yeah.
introduces this comprehensive multi-part architecture. You can apply it in different ways too, offline, maybe for optimizing a system prompt before you even start, or online, dynamically managing the memory of an agent that's running for a long time. It's built on this reflective idea that's actually pretty similar to how a really effective human learns. You experiment, you reflect critically on what happened, and then you consolidate those lessons in a disciplined way.
That sounds very much like an agentic architecture, like you're dividing up the learning work among specialized roles, almost like having a dedicated little learning team right inside the AI system itself. Can you break down those three roles? How do they work together?
Sure. Yeah, the architecture borrows from some earlier ideas, but refines them heavily for managing memory robustly. So first, you've got the generator. You can think of this agent as like the student taking the test
Mhm.
or doing the actual task. Based on the current query and whatever's in the context playbook right now, it produces the initial reasoning steps. It tries to do the job.
The doer, got it.
Exactly. Then, and this is crucial, you have the reflector. This is like the internal critic, or maybe the TA marking the assignment. It takes the generator's output trace, whether it succeeded or, maybe more importantly, if it failed, and it critiques it hard. Its job is to pull out concrete, actionable lessons, figure out the root cause of errors, generalize useful insights.
Okay, so we've got the output and we've reviewed it critically,
Yeah.
but how do we actually capture that insight? Make sure it sticks. Bottle that lightning, so to speak.
Right, that's where the curator comes in. The curator takes those structured lessons, the specific knowledge nuggets identified by the reflector, and it synthesizes them into these compact delta entries, little update packages. These entries represent the new knowledge, and they get safely integrated back into the main playbook. This three-part system, well, it stops one single model from getting overloaded. Trying to generate, diagnose errors, and manage knowledge all at once. Makes the whole learning process much more reliable.
And the context that ACE generates isn't just a jumble of old chat logs, right? It's structured, a real playbook, ready for the next challenge. What kind of specific information categories end up in this modular context?
Yeah, it's meticulously categorized. That's key to making it useful and fighting that brevity bias we talked about. The research highlights things like specific strategies and hard rules. For example, maybe when processing financial transactions, a rule might be, always check identities against the central contacts app before trying to parse names from the free text, and use standard date range comparisons. Super specific.
Ah, okay. That's immediately useful, right? No more guessing if Mike in the transaction is your roommate Mike or some other Mike.
Precisely. It also documents useful code snippets and templates, offering pre-vetted code patterns, like, say, the right way to use Python's default ick list if you need to aggregate data efficiently, avoids common bugs. And maybe most importantly for autonomous agents, it systematically tracks troubleshooting and pitfalls. Like, here's the step-by-step debug process if app authentication fails. So the agent doesn't just get stuck or waste time trying things that won't work without a valid login. It's this level of detail that makes the context so powerful.
Okay, so the richness of detail makes ACE powerful. But it's the preservation mechanism that makes it resilient. Stops that context collapse nightmare we discussed. How does ACE actually manage to grow this super detailed context without the LLM accidentally torching it every few steps?
The secret sauce is really in its core design. Incremental delta updates. Instead of viewing the context as one big monolithic prompt that an LLM has to rewrite entirely every single time, which, yeah, leads to collapse, ACE sees the context differently. It's treated as, like, a living collection of itemized, structured bullets.
Ah, so small, reusable units of knowledge, like a specific strategy nugget or a documented failure pattern.
Exactly. Tiny, manageable pieces. And when new knowledge is generated by the curator, ACE only produces these compact delta contexts, basically small, isolated sets of new potential bullets. These are localized, incremental additions. It's never a full context rewrite. This preserves everything learned before while steadily adding new insights. It completely removes that risk of catastrophic deletion.
Okay, incremental updates make sense. But wait, if we're just adding bullets all the time, doesn't that create a massive risk of just running out of space, hitting the context window limit? Like, we solved collapse, but maybe now we just drown in detail much faster.
That's a really critical point. And that's where the other part of the resilience comes in. It's not just about adding. ACE uses a mechanism they call grow and refine. So yes, new bullets get appended, we grow the knowledge, but the system also periodically refines the playbook. It cleans house. And crucially, it uses non-LLM logic for this, specifically things like semantic embeddings, fast vector comparisons, to identify and prune bullets that are too similar or redundant. This keeps the playbook comprehensive and useful, but stops it from becoming overwhelming or busting the token limit. It's a balance.
That separation, using the LLM for learning but not for organizing, sounds incredibly efficient. Those full context rewrites must be a huge computational drain, right? Especially if
Yeah.
you're doing them often.
Oh, they are. Prohibitively expensive in many online real-time scenarios. And this efficiency game, it's honestly one of the most compelling aspects of ACE. The numbers are pretty stark. AC achieved 86.9% lower adaptation latency, so much faster learning cycles.
Yeah.
And 83.6% lower token dollar costs compared to older methods like dynamic cheat sheet, specifically in that online setting.
Wow, 83% cheaper. That is massive. So the really expensive part, the big LLM brain, isn't doing the tedious librarian work anymore. It's not sorting, merging, deduplicating bullet points. We delegate that management task to cheap, fast, non-LLM code.
Exactly right. The LM focuses on the high-value stuff, generating the initial attempt, and, crucially, reflecting intelligently on the outcome. But the repetitive, mechanical job of organizing the playbook, controlling redundancy, that's handled externally, which dramatically cuts the computational overhead and speeds the whole process up.
All right, let's talk payoff.
Mm.
'Cause this is where all that clever engineering translates into real-world performance jumps. The research tested ACE across two main areas, right? Autonomous LLM agents and that knowledge-heavy domain-specific reasoning. What were the headline results for the autonomous agents?
Yeah, on the LLM agent benchmark, App World, ACE delivered average gains of 10.6% over some already strong baselines, which really shows how effective the framework is at teaching an agent complex step-by-step procedures over time. And what's really important here, it built these effective playbooks without needing labeled human examples for supervision. It learned just from execution feedback. Did the code run? Did the API call succeed or fail? That was enough signal for the reflector agent.
Okay, 10.6% gain using just execution feedback is pretty impressive.
Yeah.
And what about in that knowledge-intensive domain? The complex financial benchmarks, finer in formula.
There, where tasks demand deep understanding of specialized rules, XBRL tags, interpreting complex financial statements, that kind of thing. ACE delivered an average gain of 8.6%. And it got there by building these playbooks filled with specialized tactics, things you just can't capture in a simple generic system prompt. It learned the domain specifics.
I think, though, the most startling result, the one that should really highlight the value of this engineering approach for you, the listener, is that head-to-head comparison
No.
on the Upward leaderboard.
Oh yeah, it's genuinely a powerful case study. Shows how superior context engineering can really win. So get this. React a standard agent prompting method plus ACE. When using a smaller, completely open source model, DeepSeek v3.1, it achieved an average score that actually matched the performance of the top-ranked agent on the leaderboard at the time. That agent was IBM's CUGA, powered by the much larger state-of-the-art GPT 4.1 model.
Okay, let me make sure I heard that right, and that you, listening, caught it too.
Yeah.
A smaller, more efficient open source model equipped with this ACE context engineering reached a performance parity. It tied with a proprietary agent running on arguably the best foundation model available.
That's correct, matched it. And furthermore, on the harder part of that benchmark, the test challenge split. React plus ACE, using its online adaptation, actually surpassed the score of that production agent, beat it, that one result. It basically validates the whole ACE philosophy. It tells us the bottleneck isn't always just the raw power of the foundation model. It's often the intelligence layer you build around it. Context engineering is really becoming the new competitive edge.
Absolutely. And just connecting it back to efficiency one last time, these weren't just marginal gains achieved with brute force. ACE hit these high accuracy numbers while drastically reducing the number of expensive interactions with the environment. About 75.1% fewer rollouts compared to other reflective optimization methods. So it's faster, it's cheaper, and fundamentally it's just a smarter way to learn.
So Wrapping it up, what ACE really represents is a scalable and very efficient new paradigm for continuous learning, for self-improvement in these LLM systems. By treating context as this structured, evolving playbook, it gives you a level of flexibility, fine-grained control, and interpretability too, which is something you just don't get if you're only relying on slow, opaque weight updates. This really cements context adaptation, I think, as a central piece for building genuinely capable compound AI systems going forward.
The results really do speak for themselves. It seems like context truly is the new fine-tuning. But, while ACE is clearly incredibly powerful because it learns from specific, reliable feedback, code success, API errors, things with clear outcomes, its effectiveness still really hinges on the quality of that feedback signal. And that raises a really interesting, maybe challenging question for you to think about as you consider applying this kind of tech in a truly complex, maybe messy, real-world situation with ambiguous outcomes. Let's say something subjective like long-range strategic forecasting, where you don't know the right answer for years. How do we guarantee the quality of the feedback loop that an agent needs to actually self-improve using a system like ACE? How good does the feedback need to be?